Welcome to the organ printing course. In the last lecture, we have discussed what is required and how to bioprint an organ, and there we have discussed the strategies, the approaches, all these things in detail. So, in this lecture, we'll be discussing basically the design approach that has been used or that have been those have been used for bioprinting an organ specifically to print a biomimicking tissue structures so that we can generate or the function can be generated for that particular tissue or organs. So there are basically three design approaches that people or that researchers consider or they work on these three different approaches. Some groups may use another take another approach for when designing a particular organ, or also sometimes simultaneously one or two or maybe all three can be used while designing a particular tissue or organ and while bioprinting a particular tissue and organ. So we'll see one by one all these three approaches. Those are biomimicry, autonomous self-assembly, and mini tissues. So the very first approach is the design approach is the biomimicry. Biomimicry, the name itself is while mimicking the biological structure or the function of the tissue can be mimicked. So biomimicry meaning mimicking the biological substances or biological, in this case the biological structure or the organ. So while 3D bioprinting, most of the time we use the concept called biologically inspired engineer, where the engineering that we are using here, that we mostly that is inspired by the biological substances or how the tissue is actually organized, how the organ is organized, how the structure looks like, and how the basically how the cells are arranged or organized in the tissue or in the organ. So when we do all these different things, we mimic all these different things, then that terminology biologically inspired. So we get inspiration from that biological substance, in this case from the tissue and organ structure, organization, arrangement, all these things, and then we use the tools that is available with us, the like something like the bioprinting technologies or also the biomaterials. We use that thing to mimic those that structural detail, suppose the organization or that arrangement of that cells or materials in that tissue structure. So then by doing that, we basically we reproduce the structure of that particular tissue or arrangement of the cells or the alignment of the cells in certain cases, and also the organization of that particular tissue into the space, so that the bioprint so by bioprinting we can develop the tissue structure or organ using organ printing. Here there are some of the things uh, that are very important. Those are very important, like identical reproduction of the cellular and extracellular components of a tissue and organ. And in the last lecture also I have discussed in great detail and also have stressed on these points, like while actually going for bioprinting of an organ, then mimicking, because we are trying to mimic that thing, mimic that structure. So identical reproduction of the cellular components of that particular tissue. So like what are the different types of cells present in that tissue. So we need to check on this, like going to understand what are the different cell types present and then how those cells are organized or arranged. So when we do all these things, then actually the bioprinting or actually we can reproduce that particular structure. So the cellular arrangement or cellular alignment, cellular organization, we can reproduce those things. So that on then only we can able to bioprint that particular tissue or organ. The other thing is this, the cellular component, as we have discussed, the cellular component, right? So cellular component, how the cell, what are the different types of cells present and how they are organized, all the things. The other thing, other important thing is the how the extracellular matrix components arranged there, or what are the different extracellular matrix components present in that particular tissue, how they are arranged, and how what are the organization of the extracellular matrix components in that particular tissue. So we need to understand all these things, and then only we can, if we can reproduce, then we'll be able to recreate that structure, and also we'll be able to we can able to gain the, or gain the function of that particular bioprinted tissue or organ. Other than this is the reproducing specific cellular functional component of a tissue, of the tissues, something like each tissue has their own specific cellular component and organization of this thing. So we need to understand that, and then we need to reproduce that, something like mimicking the branching patterns of vascular trees. So like the vascular tree, if you see the design of vascular trees is unique and is marvelous. So where the the branching happens whenever there is a requirement, like certain at certain locations, at certain spaces, and certain order. So all those things we need to maintain. Suppose we are trying to bioprint a vascular tree, so that then we need to, again we need to organize that, or we need to mimic that, then only we'll be able to come up with the vascular tree. They are this thing. So they are the patterning, or the vascular, the way the branching is happen, that is not random, that follows a particular order. So we need to understand that order, and then only we can reproduce or recreate that kind of vascular tree, so that then it, then the, and if you use that vascular tree support for development of vascular tissue construct, then only we'll be able to, the, or the cells will be able to get nutrition, oxygen supply, the wherever they are present. So every cells in that particular tissue, vascular tissue construct, they will get nutrition and oxygen. So other thing is manufacturing physiologically accurate biomaterial types and gradients. Many of the times the tissue or organ, certain tissues or organs, there is certain type of a gradient present. That can be a, suppose that can be a material gradient, that can be a chemical gradient, or suppose a growth factor gradient. So those things we need to understand, what are the, suppose if it is a biomaterial gradient, what type of biomaterial is present, and how those biomaterials are arranged or organized, and that gradient, how the gradient generated. So then only we, if we can, while manufacturing that particular tissue, suppose that by printing the particular tissue, if we can accurately manufacture that kind of pattern, then only it is possible to develop the tissue structures. And the replication of the biological tissue in the on the micro scale. In the last lecture also I have discussed this, like tissue the tissue, they are biological tissue, they are present like macro tissue. There are some in the, they are in the macro. If you see the whole tissue, that will be in the macro scale. But again, if we try to understand the details, structural details of the tissue, then we have to go to the micro scale. So then again, the biological tissue has to be replicated in the micro scale to again gain the function of that particular tissue, because there are some microstructural units of all different tissues. They have some microstructural units. That is very that is very useful, or that is very much important to for their function. So we need to replicate that thing while by printing. Then the understanding of the microenvironment of the tissue microenvironment or organ microenvironment, where the microenvironment is the where the tissue or the organ in that space, how they are, how they form, what type of structures they are, and what are the different types of microstructure present there. So that can be understood better by when, suppose we are trying to see the specific arrangement of functional and supportive cell types. Like in the different tissues, there are certain cells. Those are main functional cells that do the main job of that particular tissue. But there are also certain that, so that functional tissue types, functional cell types can be either one or different types. Again, there are some cells, they more or less they do supportive, or they act as a supportive cell. So they provide support to the functional cells so that the functional cells actually can perform the job, and these cells actually can can induce, and can also produce a specific interaction, so that by which way the basically that constitutes the microenvironment of the particular tissue, and by that way, this way only, the cell, by the and you can understand, if we can correctly understand the microenvironment, then we can try to recreate that. Other than that, there are certain soluble and insoluble factors that are always present in the tissue microenvironment that can be secreted by the our cells present in that particular environment. Also, that the cells present in the surrounding environment, or maybe in a far reaching environment, also if they are present from there, also that kind of thing can the that soluble and insoluble growth factors, so insoluble factors that can reach that particular tissue microenvironment, and then they can have their effects. Something like soluble growth factors are very easy, because they can reach to any tissue microenvironment by blood supply or tissue fluids or supply. Insoluble factors, they are mostly bound factors, where they are present in the bound manner with the extracellular matrix, different extracellular matrix components, specifically to the glycosamine and glycans, and then those are presented to the tissue or presented to the cells, so the cells can get activated or to do different jobs. So with that gradient, in certain cases, that gradient is very important for this all these different factors, and depending upon the gradient also it can do. And other thing is the spatiotemporal delivery of those growth factors at the tissue microenvironment. Suppose like different growth factors appear and perform the job, and then they disappear. So that thing very important. And the other thing is the composition of that particular tissue, ECM. ECM is a very complex, because there are macromolecular substances, macromolecular components that is present, and there are more than, it's like hundreds of components are there in the extracellular matrix composition and extracellular matrix of a particular tissue. So we need to understand the extracellular matrix component, and then only we can able to successfully recreate that scaffolding of that particular tissue structure or organ structure. Other than this, our each of this tissue or organ, they they undergo or they experience different types of biological forces. Something like maybe it can be fluidic forces, it can be mechanical forces, it can be compression, tension, relaxation, or it can be bending, or it can be different biological forces. There can be some electrical signals that is conducting, or that is going through that particular tissue. So all this nature of that biological forces, we have to understand different what are the different types of forces that is acting on that particular forces. So there is also other things. There can be the gravitational force that also can work on the tissue. So that is also another important concept to study. And a few researchers actually they are targeting to they are trying to understand what will be the effect of this gravitational force at that particular tissue. Suppose that that bioprinted tissue, if we take it to some other in extra space, not in any other spaces, like in a moon gravitational force or any other forces, other other spaces. So what will be the effect of those forces on the tissue? So that understanding this biological forces, nature of the biological forces on the tissue, that is very useful, and that has to be, by this way only we can come to know about this technique. Other than this is the knowledge. Now here, this bioprinting is a highly interdisciplinary research area, where knowledge drawn from various basic researches like the field of engineering, imaging, biomaterial, cell biology, biophysics, medicine, all these are very important. So those things are, you need to understand those things, and then only we can implement the knowledge that is gained from all these different allied research fields, and that can be implemented very well implemented in in bioprinting. So these all things are very important, and there we have a role of all these different fields like engineers, engineering from different engineering fields. Imaging more different imaging modalities can be used. Biomaterials is very important because we need to use certain biomaterials for applying them to develop these tissue structures. Knowledge from cell biology, biophysics, and medicine. These all things are very very important, and we need to understand that thing in great detail. Next design approach is the autonomous self-assembly, and in this case actually self-assembly, if you see, self-assembly is when, suppose if you put the cells together, they have the intelligence when they can actually assemble with each other, and they can have the form the groupings, and then they can start the tissue building process. So that process can be autonomous, and here the clue is from the embryonic organ development, because if you see the organic embryo development, then that can organ development can be used as a guide to understand what are the different factors that helps in the self-assembly process, and how actually we can recreate that self-assembly structures using uh, using bioprinting. So the embryonic organ development can be used as a guide for this tissue development, or for the organ bioprinting. So where we can actually try to understand that what are the different process or different factors that those are involved in the embryonic organ development. Where the if you can recall, in the last lecture also we have discussed that thing in some detail, where we have discussed that what are the different organ in the embryonic organ development, what are the different, how actually that process happens, where the developing tissue that they produce their own ECF components. Like if you see at the very early stage, the cell, there are only a fertilized egg. From there few cells develop. From there the cell number keep on increasing, and then they mature, they differentiate, they organize all these things, different things happen. So developing tissue, and they also produce their own extracellular matrix components, because these early cells that is present in that particular tissue, they produce their own extracellular matrix component, and that is very helpful for that particular tissue development. So because that extracellular matrix component, because that extracellular matrix that provide the scaffolding for the very early cells, and then they can actually uh, differentiate into different cell types, and then they can produce the different tissues or organs in the whole human. Their appropriate cell signaling, what type of cell signaling present there, what are cellular interactions, signaling or cell matrix material interactions, those things are present there. Those things also we need to understand, so that we can use them to our in our bioprinting, in a bioprinted construct, so that can be, if that can be used or not. Then autonomous organization and patterning. If you see, then the early stages of this organ development, yeah, in the embryonic organ development, where the cells, they organize themselves together and also pattern themselves in a particular order, by which different organs or different tissues develop. So that process is autonomous. Certain cell signaling, certain other factors of course present there, but so we need to understand that also. And then only, because in bioprinting, organ bioprinting also, we can take clue from this, how this organization and patterning happens, and if we can recreate, that will be the most biomimicking design that can help us to achieve that goal. And also desired biological microarchitecture and function, because all these tissue or organs in the embryonic stages also, they have a typical microarchitecture, and due to that the function of the particular tissue is established. So we need to understand that what kind of biological microarchitecture present there, and how the tissue or organ the function is related to that particular architecture or the structure. That thing also we need to understand, and then only we can this thing. So there are various groups. they work on this, how this different microarchitecture, generating different microarchitecture or even nano architecture, and then understanding how the cellular responses on this different microarchitecture or this different nano architecture. So that thing, and then they try to use that knowledge gained from those experiments to bioprinting and tissue building, basically tissue engineering or tissue regeneration. Now there are another concept called scaffold free approach, because scaffolding is like when we use certain biomaterials to design or develop certain scaffolding architecture. By the way, actually our intention is to control the cellular responses. But there is another concept called scaffold free approach, where no scaffolding materials or biomaterials are used, where mostly it is the cells or the cellular assembly that help in generating the tissue structures, where the cells, they also produce their own extracellular matrix, and by this way we can that whole tissue can be developed. So here cells assembling of cellular spheroids and that undergo fusion and cellular organization to mimic the developing tissue. So here basically, as it happened in the case of embryonic organ development, the cells, they assemble together, then the cellular spheroids that produce, the cellular spheroid produced will go undergo fusion and organization to mimic that, and the new organs or new tissue will develop from there. So can be a clue, and we can also use that for bioprinting. So basically, this process relies on that the cells are the primary driver of histogenesis, or that means tissue building. So that the cells, if we can use those cells in a particular way or in a particular fashion, then only they will drive the particular tissue formation. So that in that case, they will direct the composition, localization, functional and structural properties of the tissue. The cells, they are the building block of that particular tissue. They are the driver basically, and they can direct the composition of the particular tissue, localization, functional and structural properties of the particular tissue. So these all things are very important, because these things are very important function of the cells. And in bioprinting, if we can use any of these things for our tissue development, then that will be more biomimicking, and then actually we will be successful in generating different tissue structure. Other than this is the knowledge of the developmental mechanics of embryonic tissues, genesis and organogenesis. What are the different mechanisms, developmental mechanisms of this embryonic tissue genesis and organogenesis that is present? So that also can lead to very good strategy for tissue or organ regeneration, and we can basically we can use those mechanisms for our applications. Then the other thing is if we can able to manipulate the environment of that particular in a bioprinted tissue, then we can drive the embryogenic mechanism. Suppose we understand what are the mechanisms present. Suppose like something like cellular organization, patterning, cell signaling, cell material interactions. All these things, if we can and understand all these different things in the bio, and then we can implement that in the bioprinted tissues, so for manipulation of the environment, so that a the tissue building can happen with the help of this autonomous self assembly. So this is a very important design approach. The next thing is typically the mini tissues, where researchers, they are trying to develop or trying to print smaller functional building blocks of that particular tissue. So that is called mini tissues, right? Because each of these tissue or organ, they are composed of smaller functional building blocks like this, and that when we connect those building blocks together, then actually the whole tissue can be formed. So this smallest structural and functional component of the tissue, something like a like the kidney nephron or liver lobule. So these are the functional units of of a particular tissue, and you can say that those are the smallest structural and functional component of a particular tissue, and recreating that kind of mini tissues are very important to generate the function of that particular organ. And if we can successfully do that, then only we'll be able to do generate that particular tissue or organ. Now these mini tissues that can be fabricated and assembled into a larger constructs. If we can successfully fabricate all these different mini tissues, then definitely we can able to again assemble them together to a larger construct. By one thing is by rational designing. There we need to understand the design of the particular tissue, how the tissue, like how the different units they are connected to each other. They are basically they're facing each other. They're interacting with each other. All these things we need to understand, and then that rational designing is very important, and we have to follow that. Self assembly, as I discussed in the last slide, self assembly is like when the suppose the tissue building blocks, like suppose the cellular clusters, and then if we can put them together, and if we induce a certain kind of organization interaction between them, they self assemble, and then a particular tissue can be developed. Certain cases, a combination of both can be used by rational designing of that particular tissue building blocks, and also connecting these tissue blocks or self-assembling the cells together to develop that again the small tissue blocks. So any of these approaches can be used for developing these many tissues, and then that can be used for to develop the whole building functional tissue. So there are two major strategies to develop this kind of mini tissues. Either we can work only on the self assembly, where the cell spheres will be produced. So that is the mini tissues, and then that can be put together to develop the macro tissue. In the other approach, where actually we can work on the accurate high resolution reproduction of that tissue unit. Suppose there actually we are not relying on the self assembly of the cells. Here we are putting the cells in a particular fashion, particular order, mimicking that actual architecture, current tissue microarchitecture or the cell organization. There we reproduce with in a high resolution manner, and then design them that to then that structure is present. So that is the mini tissue, and then allow them to self-assemble into a functional mono tissue. So any of these approaches can be any of these strategies can be used to develop the thing, and both are very powerful strategy, and various research groups they use either one or another type of strategy their for for the organ printing. Now the examples of these mini tissues and this examples of mini tissue with the concept of mini tissue, how the concept of mini tissue can be used for bioprinting is like when we use self-assembly of the vascular building blocks to form form vascular branched vascular network. Suppose vascular building, small vascular buildings that we can develop, and then that can be self-assembled together to develop the whole vascular network. That would be useful. Organ on chips, maybe organ on a chip is another idea where this where the different tissue, small tissue blocks, like different tissues will be developed, and then that can be connected by a microfluidic network platform, so that that different tissues can be interact with each other, and then the whole organ on chip, different organs on chip, those things can be produced. So this mini tissues is another design approach by which also we can develop the whole tissue by printed tissue, taking one step at a time. So taking the small building blocks, small functional component of the tissue that can be printed and that can be used. Now let us discuss. Let us summarize the whole this week, all the lectures of this week. Suppose like organ printing, we have discussed what are the different what is required to understand, what are the different things to be considered, and also how actually we can bioprint the tissue structures, what are the different strategy, what are the different approaches, what are the different design strategies. All these things we have discussed in great detail. So now let us in this slide actually we'll summarize all these points together, and then so these points, what are the actually points to remember for organ printing? So that is the so that basically a take home message from all these different lectures is what are the points that you should remember while actually attempting for organ bioprinting. Now, organ specific microstructure is essential for organ function. We have seen this before, we have discussed this before, that every organ they have a particular typical microstructure, mesostructure, macrostructure and microstructure, and also in the cellular level or also in the ECM level they have a typical microstructure or nanostructure. So that is essential for that or particular organ function. So structure, if we can recreate particular structure, definitely we will be able to gain the function of the particular organ. So that is we need to understand, always remember that, and we have to start, if we are targeting a particular tissue or organ, we have to understand the microstructure of the particular tissue or organ. Now, what are the different bioprinting technology we can use that should be capable of mimicking the macrostructural and mesostructural details with high fidelity? That means the bioprinting technology should have the capability to print that microstructural detail or macrostructural detail of that particular tissue. So that can be from 1 millimeter to, like, from millimeter to centimeter scale, right? That should be able to reproduce that kind of structural detail with high fidelity. That means accurate reproduction of that thing. If we can do, then only we can try to print a specific tissue or organ. Now here biomaterials are very crucial for achieving the goal of whole organ bioprinting, because cell self assembly or cellular assembly can be employed, but by this way to actually to reach centimeter cell scale tissue is very difficult. So there we need to take this approach, like this biomaterial based approaches, that is very crucial. So we need to understand what type of biomaterial, of course we need to understand what type of biomaterials to be used, what are the different, and how we can use them, what are the different ways we can use them, how we can actually recreate that extracellular matrix complexity with this both the biomaterials, that those things if we can understand, then only we can able to print, print the whole organ by whole organ. Here biomaterials that closely replicate the nanostructure and microstructure of the ECM of a particular native tissue should be employed. That means when we are trying to bioprint a particular tissue structure, first thing we understand what is the microstructure and mesostructure present in the particular tissue. What is the nanostructure of the tissue? What are the specific ECM composition is present there? How the cell, how the ECM is, suppose how the ECM is organized or arranged there in the tissue. So those things we need to understand, and then we have to find out a biomaterial. Either it can be used simple one or a combination of biomaterials that can, so they can basically they can mimic that particular nanostructure or microstructural detail of that particular tissue ECM, then only we can employ them. Designing of the other thing is this, in certain cases we may have to design certain biomaterial that can influence or promote the cell attachment, proliferation, and also self-assembly of these different cell types into a microstructure. So that is basically biomaterials driven cellular cellular assembly or cellular responses like cell attachment, proliferation, and all these things. Other thing is also directing the cells to self-assemble with guidance from growth factor and biophysical cues. So we can employ different growth factors and also certain biophysical cues like nanostructures, microstructures, patterning, suppose nanofibers, all these are different nanoparticles. So different types of cues we can provide this to the cells, so that thus we can direct the cells to self-assemble. And there is a huge body of knowledge present in this domain when various research group they work on fundamental understanding of this cellular interaction, cell material interaction, or different, suppose different topography. Based on topography, how the cellular response differ. Based on patterning, all these things. So there are different knowledge available. So maybe we need to understand the knowledge, and that can be, you can use that knowledge for particular tissue engineering. Vascular network bioprinting is another important job, or a very important requirement for to sustain the tissue function, tissue cell viability and tissue function. So because without that, the cells will not be viable in a bioprinted construct. So we need to design a vascular network, and we need to bioprint the vascular networks with the, and in this way how to improve that, because there are now there's some amount of study already exist on this particular domain, vascular network bioprinting, but how to improve that thing so that we can actually basically print a vascular tree exactly mimicking that native vascular tree in a bioprinted construct. Then only we can able to, so that the we can supply the cells, or cells can be survive in the other tissue can be, the function can be established. Other thing is this, also we need to improve the fabrication time without compromising the resolution and cell viability, because we have seen in earlier while dealing with the bioink, there we have discussed that the fabrication, if we increase the fabrication time, to improve the fabrication time, we need to come up with a very high print fidelity materials, and also probably we need to work on the rheological properties of the bioink. But we should not compromise on the resolution or also on the cell viability, because we have seen that if we can, suppose we want to improve the print fidelity, we have to improve the viscosity, increase the viscosity. And with increasing viscosity, if there is a very stiffer in microenvironment, that is not good for cell viability. So that's what we have. So we have to come up with some strategy where we can, the fabrication time can be enhanced without compromising these two things. And uh, another important thing is why fabrication time is important, because during printing, cells are in that unnatural environment. They are not, actually they are not meant to be there in that thing. So when it so during the printing process, that can be that is challenging. So if we can reduce the processing fabrication time, then we can print the tissue fast, and then the time required for the cells to be there in that kind of environment is very is also less. So that's why we need to improve on the fabrication time. There are many other points to remember, and probably in many of these different lectures I have pointed some of the things. So with all this, actually we can basically, if you have these knowledges, then we can start doing different organ printing. So, so in the from the next lecture, I will be discussing some new concepts on this organ printing. Also, I will start discussing few strategies that are, some strategies those are used for bioprinting of particular tissues and organs. Thank you for attending this lecture. So we'll again see you in the next lecture. Thank you very much.